let's carry on. So, yeah, we've just got this weird bit of syntax, which apparently has become kind of what's the word? Idiomatic in Julia. It's called short circuit evaluation. I don't particularly like it, but so if I put a equals 3, then I can write a less than 5 and, with 2 ampersands, print line small. And what it will do is an if-then. So if a is less than 5, then it will print small. Why? Because it's a logical and so if this thing is true, then it will evaluate the second one. If it's false, then it won't evaluate the second one because it just short-circuits the evaluation, and that's what the name is, why the name is. And similarly, I can do if not, then with or. So this is used all over the Julia code base, and it's become idiomatic in Julia. So it's just a really quick way of writing if-then. There's also the ternary operator. That's the same as C. Ternary because it has 3 arguments. So if A equals 3, then, I don't know, jump for joy. Print line hello, else print line not true. So I never actually evaluated the cell. Okay, A equals 3, so it does print hello, right? So if you're not used to those pieces of syntax, then they're useful to learn because they really appear all over the place because they're just a short way of saying if something, then something else something, which in Python becomes sort of 17 lines, all right, something like that. Okay, so yeah, as I said, we can do array comprehensions just like in Python, but it's a bit strange because in this case, we're getting an array of any out, so I'm not actually sure why that is. That's a bit strange. I think you're supposed to get oh yeah, okay, that's strange, yeah. So if I just do the range, it knows what all the types are going to be, but if I add this extra thing onto the array, apparently it doesn't know anymore what it's going to be. And it puts an any in there. Okay, a bit strange. And I can do very compact, create matrices in a very compact way with array comprehensions. Right? So actually, probably that's the good answer to your question. So let's try that in 3 dimensions. Sums I plus j plus k for I equals j this, k equals 1 to 5, and it gives me a 5 by 5 array. 5 by 5 by 5 array. That's a very neat way of creating higher dimensional things. Right. Okay, so matrices, as I said, we have this nice MATLAB syntax. And so just like in Python, we can extract the columns, everything is the same. Okay, so what about multiplication of matrices? Oh, so first of all, random numbers. The Mersenne twister, just the same generator of pseudo-random numbers as in Python. So the rand function, again, you don't have to import anything, produces one random number. Rand 5 generates an array of 5 random numbers, uniformly distributed between 0 and 1, and rand 5, 5, a matrix, and rand 5, 5, 5, a 5 by 5 by 5 array. So rand tab will give me a list of all the rand things I can do in Julia, right? At least in base Julia. And then there are packages, of course, to do more complicated things. So there's the distributions.jl package, which has a list of, has much more probability distributions. So So matrix multiplication, this is pretty neat. So there's been this recent development in Python with the @ operator, which is pretty horrible for matrix multiplication. So as we said, we can't do times for a vector with a vector because it doesn't sort of make any mathematical sense. But what about a matrix and a vector? Right, so in NumPy we would do .mv, and that doesn't work in Julia because, well, you could define it, right? So how do I do matrix multiplication? Well, I really do just use the times operator because now it makes mathematical sense to do that. And there it is. M times V does the matrix multiplication. And so if we look at the methods for times, then we can try and work out which... We can try and look through all these 100 methods to work out which one it might be using to work on this array, to act on this array. But there's an easier way, which is at which A times B. A times what? No, M times V, sorry. So what's going on here? So is that going to work? Yeah. So that tells me, what that does is tells me which exact function with which exact type signature, which exact combination of types this operation is going to call. And it gives me, as usual, a link to exactly the definition of that thing. And so what's this at going on? It's a macro. So which is a macro, and so I have to put this at thing there. So what is a macro? It's sort of, we can sort of think of it as a glorified function, a much more powerful function. So it takes an expression and turns it into an expression. So because it's doing something kind of complicated involving code generation, it needs to be a macro instead of a standard function. So we can just use it as if it were a super function, but we'll see a bit later what's going on a bit more behind the scenes. So what does this matmul do? Well, it does a mul bean, so then you have to go and look up the definition of a mul bean. It's doing some blast thing underneath, right? So basic linear algebra subsystem for those non-linear algebra people. Okay, so you don't necessarily want methods all the time. You can use this at which instead. Okay, so I've got another little exercise, a bit more interesting maybe. Use the power method to calculate the largest eigenvalue of the matrix, this matrix. So we start from an arbitrary non-zero vector and repeatedly apply m to it, which actually calculates the powers of the matrix m applied to this vector, and the resulting vector should converge to the eigenvector, will converge to the eigenvector with the largest eigenvalue. So it's a kind of neat thing to try, if you want. If you want. Try and do that in Julia. It's supposed to be a hands-on tutorial, right? So I had to invent these exercises. And do ask questions while people are doing that. The question is there a general tensor contraction? And I was reading about that the other day, and I don't remember what the answer was. Oh, I was hearing about it the other day. There's some tensor package. Yeah, tensoroperations.jl package. That's the answer. The answer is write it, right? I think I have to speed up, so we started at 1, right? Yeah, okay. Shall I do it? Are we ready, or more time? Nobody knows. Okay, so let's start with a non-zero vector W, which is a two-dimensional vector if we have a 2 by 2 matrix, so let's choose 1, 1. With a comma, and then I want my matrix, so 2, 1, 1, 1, and well, we better use floating point just to be on the safe side. Reshape that to 2, 2. Let's just check that we've got the right things. So M and W. So that's a tuple. No, like in Python, when I do something comma something, that gives me a tuple or a tuple. Ordered thing. Okay. So now what do I have to do? I have to apply M to W, and we saw that I can do that with the times operator. I don't think I can do it with a C dot. Nice syntax. but maybe I can. No. No, I don't think so. Okay. So there's already one nice syntax. Why do another one, right? So just going to apply it several times. I want a for as a first step for e in 1 to 10, sort of, let's call that W0, well, whatever. W, yeah. So W0 is 1, 1. W is W0. I guess I need a copy, probably. No, it's not like that because we're not doing Python. Copy that. So I'm just going to apply M to W, and I'll call that W new. And then I just maybe print it out, and then feed it back into W. Sort of standard thing. And of course, what did I forget? End. So what's happening? So this vector is just exploding. So that's no good. So what do I have to do? Normalize it. So W equals W new over the norm of W new. So this is definitely the neatest, most readable code to do this algorithm that I've ever seen, right? I think. I mean, it really looks like what it's saying. And we see that indeed it converges pretty fast. So let's do it a few more times. And it's really converged to something, and that's going to be the eigenvector, right? So let's just check that we're checking that it's the eigenvector because what we're doing is taking this vector, applying the matrix, normalizing it, and it gives me back the same thing. So actually we see that there's some floating point nonsense going on. So it's not actually converged to anything, which is a bit unfortunate. But we just have to stop it with a tolerance. So let's put tolerance equals 1 e to the minus 10. So instead of the for, we'll have a while. So while the distance between, so let's put W new equals 3, 3. While the distance, so the distance is going to be sort of the norm of the distance of the difference between W new and W. It's bigger than tolerance. I'll do that. And so it should stop at some point. Otherwise, it's just going to crash my machine. Yep. Oh, because I'm changing W new as well. Oh dear. Yeah, I needed W old. Okay, anyway. Okay, so that's not going to work, and it's really crashed. Of course. Just what I always needed. Yeah, sorry about that. So yeah, so I guess exercise, do it properly. But so we can see that the syntax in Julia is really nicely defined that you can really do all the mathematical things in just like as if you were almost just like you were writing the code, writing a pseudo algorithm by hand. Oh, come on. Oh yeah, thanks. Yeah, so Julia is designed. I mean, they had in mind scientific programming, but it is designed as a general purpose programming language. So they ultimately desire to sort of become solved with stuff like Python. Sure. Yeah. So at the moment there are a relatively small number of packages, but as we'll see, hopefully you can call. I mean, that's part of the idea of being in this workshop that we can call Python from Julia to fill in all the sort of functionality gaps, but there are sort of already HTTP servers and I don't know, whatever. I mean, I don't really know that side of things, but yeah, there's a lot of like, sort of general purpose stuff. Yeah. Okay. Right, yeah, there's scope going on, yeah. So This is when we need the need a table of contents for the notebook, right? Which exists in Python but not in Julia, I believe. Okay. So I think I actually lost all the code because I didn't save it. Anyway, so yeah, so there is a scope thing which I didn't remember. Let's see, for I equals 1 to 10, t equals 3 end, so I shouldn't be able to see t outside. Is that right? Yeah. Okay. So linear algebra, so instead of calculate, so this is the way that Google calculates, or at least used to calculate, the eigenvalue of their Google rank matrix, this method, or sort of a variant of it. But if we want to do something more serious, we're not going to write it by hand, we're going to call out to LAPACK, which is the sort of standard linear algebra package. So, okay, so let's do that. So this is the latest version. So if I generate a random matrix of 100 by 100, I can do various linear algebra operations on it. So I can do, for example, eig of m, and it'll just calculate the eigenvalues and eigenvectors of the matrix, just like in NumPy, SciPy. And they're complex numbers in this case, because it's just a random matrix. So that's using LAPACK. But now there's this really pretty neat thing that they've recently been incorporating, which is not, they haven't got to eigenvalues yet, but there's this thing called the LU decomposition of a matrix, which writes, oh, that didn't work. I've got some problem with my internet, apparently, but, so the maths is only rendered if you have access to the MathJax thing, and something's going wrong with that. Okay, so there's some formulae in this bit. So the LU decomposition just writes a matrix in terms of a lower triangular matrix times an upper triangular matrix. Is kind of a equivalent, it's like a version of Gaussian elimination. So what I'm doing here is taking this random matrix and then map, just like in Python, maps this function on every element of M. So there's various functional programming tools in Julia as well. So let's just have a look at what that looks like. So it's just going to convert every element of M to a big float. So it's not a very clever thing to do because we're going to lose some precision and whatever, but just an example. So now we've got big floats, which by default have 256 binary digits of precision, and we're going to actually do the LU decomposition on that big float matrix. So this is something that's written in pure Julia. So it's basically they took the sort of textbook algorithms, wrote them in Julia, and they just apply to any type. It's just absolutely fantastic. So, but when it's doing LU on a real floating point matrix, on a standard floating point matrix, it does use the standard LU stuff. So let's have a look at that. So what are the methods for this LU function to do this decomposition? Here they are. So there it is. So let's... So there's something really weird going on with the internet. It's just slow. Very, very slow. Okay, so that's not going to work. So we can actually see the local version of that code if you have it sort of installed in the right way with this @edit macro. So that's like @which will tell you which thing it's doing. @edit will actually open an editor, so it opens the world's worst editor, unfortunately. I don't know how to change that, but there is some way. And so here is all the LU stuff. And so basically at some point it decides, is this a floating point matrix, in which case I can call this super optimized library, or is it not, in which case I'll just do the Julia code. So it's a pretty amazing example of how you can really write numerically intensive code in Julia, and it's pretty fast. I mean, so if you do 1,000 by 1,000, it's not fast, but 100 by 100 still works. Okay, so you can, questions? So you can interact with the system, so you can do command line arguments and files and stuff. Kind of want to skip that because it's not very exciting, but you can read it later, if that's okay. Oh, so, just like in NumPy, there's these write DLM, that means delimited. So you've got, okay, so maybe I should do it. So you've got some array, and you just write it to a file with this function write delimited. So it's just going to sort of, oh, goodness sake. Confusing. What happened? Busy. Yeah, that's the... No. Oh, for goodness sake. I'm sorry? Yeah. Right. Yeah, okay. What is it about never doing live demos? And, yeah. So, what was I saying? Yeah, so this write DLM just, it's like save text to NumPy, it will just dump it straight to the file, and you can specify a format. Yeah, and then you can read it back in with read DLM if it's in, some just a block format with some tabs or whatever, or CSV, I guess. Not sure. You can read it in. So that's neat. And, there's sort of read lines. So to open a file, use open with a standard syntax, and then read lines. You get some strings. You can split the strings with map, and then you can extract things just like you would in Python. So yeah, there's this semicolon operator again for sending things to the shell, but actually there's something much more powerful in Julia, which is backticks. So I haven't prepared anything particularly on that, but there's a really good description in the manual. So echo hello. So that's a thing in Julia, which is like a command thing, and then I can run it, and that'll send it out to the shell, and the shell is bringing back hello. And then I can capture that output and do things with it. That's all in base Julia. There's a good description in the manual. So, okay, so questions? So now we're getting to sort of the more interesting stuff. So that was like the basic syntax that you have to get out of the way. So let's think about functions again. So let's define a function. So I don't like this one. Let's do duplicate. So duplicate x will just return 2x. So you don't need the return, you don't need to write explicitly return. The last thing in the function is what it returns. As we've been seeing, Julia always returns the last thing. And so this is the other syntax for functions. So I could put, dupe of x equals 2 times x, or 2x even. Function duplicate returns 2x. I can, they're the same. They have the same functionality. So let's do duplicate x. Oh yeah, I already said that, yeah. Okay, whatever. So, okay, I shouldn't change the thing in mid-flight, right? Yeah. So duplicate 3, I can duplicate 3.5. I can duplicate a complex number. So as in Python, I haven't specified the type of x. It's duck typing. It'll just work with whatever type of x I can multiply by 2. But we see that I can't duplicate a string. Right? Why is that? Because there is no string multiplication by a number. So that's different from Python. So it turns out that in Julia, they decided that instead of string concatenation being plus, it would be times, because it's non-commutative. And so you can do hello to the power 2, and it'll duplicate it. Right? But if we try 2 strings and summing them, then that method doesn't exist. So what does that mean? It means that the plus function has no sort of instantiation with passing it 2 strings. Right, so again, we can see what plus does have with methods of plus, and if we scroll down, we won't see 2 strings. So what can we do? Suppose that we're, sort of Pythonistas who like having plus for adding two strings instead of times, can't get our head around it, we can just define it. Just define a new plus. And so we're going to put plus of S1 and S2, and we have to specify with this type specification that we're adding the two strings. Okay? And so there's this notation string of something, something, and something, and that'll just make a string by concatenating everything, actually, it turns out. So if we do that, then we've added a method to the plus function. So before it had 123 methods, now it has 124. Right? So I just added a new sort of type of plus with these two new, this new type signature that I have never seen before, and that is not ambiguous with anything that's already there. If it were ambiguous, then it would tell me, right? So I could do, I haven't tried this, so let's say plus S1 plus A, which is a float, 64, with B, which is an integer, int 64 maybe, right? So that collides with some other things that are already defined. So let's try that. I don't know, whatever, A minus B, right? Oh, no. Yeah, so that warning that's getting truncated apparently is telling me that it collides with something I already defined. And I've already, Sorry? I don't think you can remove a method, actually. Yeah, you just kill the kernel, yeah. Okay. No, well, but killing the kernel doesn't work either, apparently. Oh, this is not good. Are there any IPython experts in the room who could help me out here? No. Okay. Oh dear, sorry about that. Let's try again. So one of the things I realized while I was preparing this tutorial is that there is no easy way to split an IPython notebook into two parts currently. You can sort of do it by hand. Oh yeah, so then I was told yesterday that there is, you can duplicate it and then delete cell by cell one half of one of the files and the other half of the other of the files. That didn't strike me as being a particularly great solution, but certainly works. Okay. Okay, so yeah, so let's carry on with defining these plus things without running the cell that was bad news. So I'm going to define this plus for two strings. Okay, there it is. And then, but what happens if I now take a string and try and add an integer? It doesn't work because that's not defined. So let's define that as well, right? A string with a number is a string with plus, so using this plus that I've just defined for two strings, the string which is substitute the value of x in the string. And then I can do the value of x plus 3, and it works. And it works for any number, right? So actually I can do something really general. The string with anything gives s plus the string representation of that thing, right? Assuming that it has a string representation defined. So I can do, well, that's not a good example because it's already a string, but I don't know, plus the array 3, 4, 5, and it just works, right? Just gets the string version, the string representation of that and adds to it. So this is multiple dispatch in action. So it's really not a difficult concept, I think. It's just, you just define versions of the function which take different type signatures, take different combinations of types. You just specify the types. You just make sure there's no collision with anything you've already defined, no ambiguity, and then you can just use the functions, you know, on those types. Is that clear? Yeah.
Isn't there ambiguity because of the fact that we have something that operates on a string?
Yeah, good point. But yeah, so what it does is if there's a more specific one already defined, then it uses that one instead of the generic one. Right, so here x is just anything, but it already has string plus string and string plus number. So let's try that, actually. So I'm going to change the definition of string plus number to do 2 times the number, right? So the value of x is 6, right? So not a very good idea, but I can do it. And then I still have this generic one, which just does the string representation so that it works with an array, but when I do a plus 3, it still gives me a6, right? So it really knows what is the most specific one. So how's it doing that? So there's this type hierarchy. So number, what is number? It's the thing called number. It's the type called number. So the type of number is a data type. And there's this hierarchy of types. So we have like int64. So the question is, what is that kind of a subtype of? So there's this concept of subtype, but not of inheritance in the same way as C++ or whatever. So int64 is a type of signed. Is a subtype of signed number. A signed number is a subtype of an integer. An integer is a subtype of a real. A real is a subtype of a number, and a number is a subtype of any. So any is at the top of the hierarchy, and it's anything is a subtype of any. Everything is a subtype of any. And so these are all abstract types. You can't make a thing of type integer, but it's just a way of saying that, just allowing integers in your calculation. You can just specify the type signature using the 2 colons integer, and then you will only allow anything that is a subtype of integer. And you can create a new type that's also a subtype of integer. Is that clear? So it uses this hierarchy to work out, I guess, what's at the base of the hierarchy, and what's the most specific version of the function that it should be running. So a function ends up being a patchwork, a sort of quilt, a combination of different methods that maybe partially overlap but not in a bad way, and it just chooses the right one in a clever way, efficient as well way, to do this multiple dispatch to choose the right version of the function. And that is that is one of the features of Julia that's sort of different from most other languages, and very natural for a scientific programming context, scientific computing context. Okay. So I guess I didn't have an exercise ready for that. Questions? Okay, so we can define types in Julia. So all of these, well, okay, so let's look at that. So all of these types that we've been using, rational numbers, complex numbers, they're all actually defined in Julia. So we can... The what? IM? Oh, it just means for im is like for I, the imaginary part. Yeah. It's just so I don't. If you just put im, I guess it means one I. Yeah, just means I. But they didn't use I so that you could use I in your code, right? Okay. Yeah. So an interesting example is this rational thing, right? So let's say at which 3/4, and it should give me the link to this thing, and I'll hope that it's going to work. No, I won't hope that it's going to work. I'll just look at my local copy. So we're in the Julia source tree. There's this thing called base. So in source are the C files to define the language, and in base is the base Julia code. So that's all Julia code with .jl suffixes. So we can open rational.jl, and we see the code that defines rational numbers. So here are these divisions. So how do you make? So what does it mean to divide an integer by an integer? It means make a new rational number, sending it the numerator and the denominator. And so what does that do? So you have to go up here and say, where is that defined? So it's defined here, rational of numerator and denominator. So what's going on here, there's some parameterization by type going on. There's n is of type t and d is of type t, and t is a parameterized type. I mean, it's a type parameter, sorry, inside this thing, right? So the type rational, this is the definition of the rational type. So it's a special type called an immutable type, so you can't modify something in a rational number. And it's parameterized by a type t. And that type t has to be a type of integer, a subtype of integer. Right? That's why we couldn't do rationals of floating point, because it's just right there from the start. They're only allowing rationals with integers inside. An irrational with integer components is in itself a subtype of a real number. Right? A rational is always a real number. And so this is telling you, this is stating that any object of rational type will be a real. And so when you write a function that accepts a real, it will take a rational. That's the point. And what does it have inside? It has a numerator of type t and a denominator of type t. And this is a special kind of constructor that checks that you're doing everything okay, called an inner constructor. Then these are the outer constructors. So they're other ways of defining rational numbers. So I can just give it an integer, and then it just creates a rational number with n, and the unit value with the same type as the object n. So in this case, a unit integer. 1, the number 1. And that is the definition of the rational type, right? And then with these definitions, and you can define the sum of rational numbers, the product, that's all defined in this file, in Julia. Right? That's what I mean when I say that everything, the standard library is defined in terms of Julia code itself. And you can just go and modify that if you don't like it, or add something to convert a floating point number to a real number, to a rational number. I think there is a function that does that. I don't remember what it's called. Is that clear? Yeah. Yeah. So, right. So when it's outside the type definition ends here with this end. So that's the complete sort of definition of the type. So because it has no real methods inside. The only sort of method that we're defining inside is this constructor to construct a new object of that type. So that's called an inner constructor when it's inside. So what does that do? It actually does some sanity checking, right? So if either of these things are 0, if both of these things are 0, then it gives an error because that doesn't make sense as a rational number, 0 over 0. Otherwise, it simplifies. So it does a simplification. So 6 over 4, well, that's the same as 3 over 2. And it does that using this GCD function, right? Greatest common divisor. So it sort of, at the moment of construction, it does some sanity checks and then reduces it to some standard form. And then this new function is a special function that creates an object of that type, with these entries. So that's it's like it's sort of like the standard constructor in C++. And these are sort of other versions, right? So now I'm seeing how to construct a rational number just with an integer. So I can just put, what happens if I send to the rational constructor the number 1 or the number 3, it will construct the rational number 3 over 1. So I have several different type signatures that I could put in there, and they're all defined right here. So this is multiple dispatch again in action. Good question. Is there a difference between this and the internal constructor? I mean, I guess the fact that it's there means that I can't delete it. But I can't, in this moment, think why it's necessary. Yeah. And so there's this promote going on, which means, so this is interesting. So what's going on here? Here I've got rational of n, which is an integer, and d, which is an integer. But they might be different kinds of integers. There might be an int 8 and an int 64. And so what I'm doing is promoting the lesser one to the bigger one, and then constructing the rational now that they're the same type. And this dot, dot, dot is called the splat operator that expands. It's like the star in Python that expands its things, expands its argument, as the necessary number of arguments when I send it to the function. Okay. Okay, so just want to do a sort of simple example of this, right? So just a two-dimensional vector. So that's something I use in my work all the time, just a point moving in 2 dimensions, right? So I want to define a point particle which is going to have a 2-dimensional position and a 2-dimensional velocity. So without scrolling down any further, can you do that as an exercise? Define a particle type with, so exercise. So this is the definition, or a possible definition, a very simple one, of a 2-dimensional floating point vector, right? Just has 2 things. So I could do that with an array, but it turns out that that's actually very inefficient. So I really want a fixed size array, and that's something that currently does not exist in Julia, but is going to be added. I mean, there's a package called immutable arrays, but it's going to be added to base, but still not there. So it's actually, I mean, my code sped up several times, several-fold, when I switched from using arrays to these fixed size vectors. So exercise, so now that we've defined this sort of 2-dimensional vector, define a particle type with a position and a velocity in 2 dimensions. And also define, mathematical operations on vectors, right? On these vectors. So first define the mathematical operations and then do the particle, I guess. So that's all downstairs in the notebook, so don't scroll down too much. Is that clear what I want you to do? Define class and define the standard mathematical operations on this new vector type that we're defining that doesn't exist in Julia. And then use that to define a thing called a particle that has properties. And then what we're going to want to do is define a function called move that, given a particle, that acts on a particle to move it. Right? So it has a position, it has a velocity, so we're going to give it to move it sort of over a time delta t. Let's say delta t. Okay, so exercise. Oh, sorry, I should comment about this word immutable, yeah. So that means that I won't be able to go in and individually manipulate the elements of this object. So if I replace that word immutable by type, then I can manipulate them. So what's the difference? Why would I use immutable? Because it means that it's actually, the data is stored consecutively in memory instead of being boxed, instead of having pointers to the objects. So that's going to increase my efficiency as well, at the loss of not being able to actually go in and change the object inside. Questions? Yes. So if we just define a type like this without any constructors at all, it just works. So what does the constructor do? It sees if it can sort of massage this information to fit in this form, and indeed it can, and so it constructs the element. So it's interesting that actually, yeah, that's right. Whereas if I try and now do a vector 2D and I give it a complex number, it can't do it. Because I restricted this definition to only being able to use floats. So how can we define plus, for example, for this type? So let's call V this vector, and W another one, 5, 6. So if I try V plus W, what does it do? It gives me an error, because plus for vector 2D and vector 2D is not defined. So what am I going to do? Define it. Plus V, that's a vector 2D, and W, that's a vector 2D, and how am I going to define it? It's going to be a new vector 2D, right? So I'm going to create a new vector 2D object. I'm going to put v dot x. So the elements of this object, even though it's not an object like in Python, I still refer to them as v dot x. Well, I mean, the sort of the variables that exist inside the object are still accessible with this v dot x notation. Just there are no methods inside the object, right? Plus w dot x and v dot y plus w dot y. And so now I can do this vector sum. So it's a very natural notation for scientific computing to be able to just define these sort of new plus operator, or new meaning for the plus operator with these new objects that I've just defined. And then I can define, times of v, which is a vector, and lambda, or whatever, alpha, which is a number. If I want to be really neat, I can do it like that. Alpha, which is a number, and it's going to be a new vector given by v dot x times alpha, and now I regret it, and v dot y times alpha. And then I should be able to do 3.5 v times 3.5, and it works, but 3.5 times v doesn't work because I have to define it the other way around as well. Right? Okay. Right. So, yeah, I can't go back here and reevaluate this cell. Okay, I can. That's strange. That's what you're trying to do, right? You can't, yeah. Not sure. Yeah, so you have to restart the kernel, unfortunately. Yeah, so that can be got around by putting everything in a module and importing the module, and then you can change the module instead. But if you're doing it sort of interactively, then you can't do that. You can't redefine types. Yeah.
So with regards to these methods,
Yeah.
so the plus, maybe plus is a better example. There's 120.
Yeah. Yeah.
Did someone go through by hand and define each of those?
Sure. Right. So some of them are defined by hand, and you can just go and click on the things, and you can see plus of this type with this type equals this. And some of them are defined using this metaprogramming, which is, you might want to define, I don't know, for vector 2D, for example, plus and minus are going to have the same definition, except you're going to replace plus with minus, right? So you don't really want to have to do it by hand. You could just say, for both plus and minus, define this thing, right? So you could do it programmatically. So a lot of them are defined like that. So to do that, you have to use this metaprogramming stuff that we'll see a bit, hopefully. Yeah, good question. Okay, so there's an equivalent of the Python repr, or however you pronounce it, method, which is, to give a nice way of printing out these new objects. And so it's using this show function. So that takes an object of type IO in capital letters, input output. So it takes a thing called little IO of type IO, and I'm going to define that for all kinds of things, right? So if I just put show, there's 89 things that can be shown at the moment. I'm going to define how to show a vector. So I just print to this stream, it's like a stream in C++, IO, and then some representation, some nice representation as a string that I like of my vector. But to do that, so if I try and do that, it says there's an error. I can't just define show. So it says that the function base.show, so there's this sort of thing that's already defined in the module base of Julia, which is this module that contains all the stuff which is in base Julia in the sort of standard library, must be explicitly imported to be extended. So what I'm trying to do is sort of extend this method, so I actually have to put import base.show first to be able to extend it in this way. And then I've got a new method, and so when I put, v, now instead of printing out the vector 2D stuff, it prints out this nice representation. Yeah, so, and I didn't have to define the show before I defined the object, right? This show is new, but it just sort of picked it up and used it when it had to. Yeah.
What's the difference between using and import?
Yeah, good question. So, yeah, so using will import is like from something, import asterisk in Python. So it's going to bring all the names that are exported from a module and put them in your namespace. Whereas import just puts the name of the module that you're importing in the namespace, and then you'll use that name dot something to refer to everything. I've got that written down somewhere. There was another question.
So we didn't, I don't remember us doing this for class or something like that.
Yeah.
Something specific
Right.
to the base function.
Yeah, I think automatically you can do it with the arithmetic stuff, but not with other things or something.
So in general, you have to.
In general, you always have to import the thing before you can extend it, yeah. Usually you do all this in a module where you define your new type, as we were saying before, rather than just sort of on the command line, let's see. Okay, so here are the definitions, right, that I've already written down, okay. So now how would we make a particle? I don't know. So yeah, so we could do the same thing, but instead of fixing it to be a floats, we could make them any, we might want to put any kind of types in this vector, right? But they'd better be real numbers, at least for the moment. So that's the same parameterized thing that we were talking about in the rationals. So I'm going to have vector 2D that's parameterized by a type t that has to be a subtype of the real numbers, and then it's going to have an x, which is a t, and a y, which is a t. And now I should have a problem with redefining the type. Yes, invalid redefinition of the constant thing. So I'm going to restart the kernel. That's control M00. If you don't know. And so now I've got this parameterized thing. But I still can just start creating these things, these vectors, right? So now when I create this vector with 3-point and 4-point, it's now a vector 2D parameterized by float 64. So automatically it picked up that these were float 64s. But if I try it with an integer and a float, it doesn't work. So that's what this promote thing was in the rationals to enable this kind of thing to work. But I could also do a vector with any kind of reals. So I could do it with rationals. And there we've got a vector of rationals. And I need to redefine the show to make it work nicely. Oh no, I need to define it for this parameterized version. So I always forget how to do that. I think it's show, you put the parameter here, and you put the parameter here. And then it works. Right, so this is like a parameterized version of the function that, because it needs to know that there's a type parameter going on. So what's going on behind the scenes is something like C++ templates, that every time, I created, there's a vector 2D with a float 64 and then vector 2D with a rational. They're actually two completely different types, and all the functions when I use the functions, they're kind of created on the fly and compiled, specialized on those types, and so it's really efficient. Well, it is some kind of stream object, and you can write to it, and that's all I know. Yeah, sorry. Okay, so how would you define this particle with a position that's a vector 2D and a velocity that's a vector 2D? So it's just something like this. Type particle position, which is a vector 2D, and now I've got my parameterized version. Let's just put a float 64 in there. And then how do I move a particle? So I'm going to move a p that's a particle with a delta t that's a real number, and it's just going to be p dot position plus equals p dot velocity times dt. No, there are no member functions. This is how you define move. Yeah, this is sort of this change of paradigm completely from member functions to what do you call it? Multiple dispatch. Right. So we'll see an example of that in a minute. Yeah. So it's really a big change in how you think from Python to this. But once you start thinking like this, you won't want to go back to the Python way. Well, it's just different. Okay, so what happened here? So if you're used to Python, you can define plus equals. Actually, you have to define plus equals separately from plus. But in Julia, plus equals just literally means A equals A plus B. And so once you've defined plus on the vectors, plus equals already exists. And so it does define the move. I'm sorry? No. No, plus equals has to mean plus equals. I mean, what else would you want it to mean, right? That's true. That's a good point.
There's also always the risk of there's issues in parallel processing. If you have a piece of memory that's shared, you're doing plus equal, and if two processes are doing plus equal on that.
Right. Right. Yeah. Good. Yeah. This is all true. Yeah. So, but you can't, as far as I understand, you can't separately define plus equals, so you have to do something that takes account of that when you're thinking about how to define your operations. Right. So let's just define a show for a particle as well, right? So this is multiple dispatch again. I'm just, now that I'm defining show for my particle, that's instead of doing particle.repr, right? So if I define a particle, then I can't do it. So everything needs to be floats. So I'm just passing in this vector 2D into the constructor that it automatically made for my particle type. So I can construct it, and then I can move it in time 0.1. It starts at 0, 0. It has velocity 1, 1. So when I move it for a time 0.1, it doesn't work, of course. Oh, because I haven't defined it because I restarted the kernel. So it's a bit strange that you have to put these T's all over the place. I'm not sure that if you actually have to put them, I think you maybe don't. No, it works. Okay. Right, so now the next step is to define a gas, which is going to be a collection of particles. And then I'm going to have move of a gas. Right, so I can move a particle or I can move a gas, just like I could do p.move and g.move in Python, right? But it's just the point is that in Python, one object always owns the member function. So if you're doing, you're defining add of two vectors in Python, you have to do it as A is self, and you're adding some other thing that's other. But I mean, mathematically speaking, there is no difference between A and B there, and you're sort of forcing it onto one of forcing the type analysis onto one of the arguments of this function. And here it's just all out in the open explicitly. You just check the types of all of the things and define your specialized function. So maybe we won't. Well, do you want to try and define a gas? It's a bit tricky, actually. So what is a gas? It's just a collection of n particles. So you're going to have, you want to send a number n as the argument. So you're going to have so what's going to be inside your gas? The number n of particles and some list of particles, some collection of particles, so an array of particles. And then the constructor is going to have to take this number n and generate your n particles in that moment. So I think so I actually struggled with this when I was writing the tutorial. So I'm used to doing it in Python, but doing it in Julia did cause me some grief. Yeah. Right. Right, so that you can put everything in a module and just put using every time. Okay, so the file. So let me use the vector2d. Well, actually, I think I included in the repo in the repository. I think I included. Where is it? Yeah, there's this vector2g.jl that I actually use in my production code. So it's just a really stupid thing. I mean, it's just what we've just been doing. So this is how you would write it as a module. So I don't understand what. Oh yeah. So you put module, the name of the module, and then you have to put what you're going to import from base that you're going to modify, and then what you export, so the names that will be available for the people who write using vector2d. And then the definition of your type, the definition of the member function, the definition of the methods that act on your type. So here they all are, and end. This end is for the module. And then you're going to put using vector2d. You can go and modify this code, change the definition, and put using vector2d, and it should update the definition of the vector2d type. Yeah.
Does it have a mode that does not involve recompiling everything? Or everything always compiled?
No, everything. When you change it, you have to recompile it.
I mean, like, does it have an interpretive mode?
So it's a combination. No, it's always compiling everything. I mean, it's always compiling everything, but it caches the compiled. It only compiles it the first time.
Sure, well, I understand that.
Right.
But, I mean,
But it shouldn't be slow. I mean, it's pretty fast.
well, it depends on how fast you
Yeah, okay, so that's true. Yeah, that is true. When you include, we'll see that later, when you include complicated packages, there's a sort of few seconds delay that gets frustrating. That is actually, something that they're, of course, very worried about and they have very present. So at some point, there used to be, even when you were starting up Julia, there was a several second delay, and everybody was, saying, well, this is never going to work, right? And so you can now pre-compile all the stuff that you need, like the base stuff is all pre-compiled, and so that's really fast now. But so the next step is to be able to pre-compile arbitrary packages, and that's still a step away apparently. You can sort of do it, but not completely or something. Okay. Yeah.
Here, like plus, minus, you have to write the same thing twice.
Yeah.
Isn't there,
Right, that's what I was saying before, yeah. So I'm writing plus and minus exactly the same thing, but switching plus and minus here. So that sounds like something I should be able to automate. And yes, I can, and that's what we'll see later with the metaprogramming macros. Okay. So how do we do this gas thing? Okay, so So what is there going to be inside this gas? Oh, you don't even need to store the number of particles. You just have a list of particles, or an array of particles. So I can write that as a vector particle. That's the same as writing array of particle with one dimension. It's just another name for that. So there's a thing called type alias, where you can just give another name to a complicated type, just like in C++. And so then this gas function, so this is the constructor of the gas. So it's going to take an argument, which is an integer. And let's put integer here. So int is an abbreviation for int64. But integer is this generic type, generic integer, like abstract type that is the supertype of all the kinds of integers. And so I'm going to make a list comprehension of particles. And what's it going to look like? So I'm going to construct a particle with a vector 2D that I create with two random numbers, which I have to expand with this splat thing into my two components that I pass to the constructor of the vector 2D, another one for the velocity, and that's going to be for I from 1 to n. So that's how you can construct sort of these n particles, right? And then I can just print them out in a show of a gas. And so when I create a gas like that, it just sort of prints out the particles, and then there's a move. There should be a move somewhere that's got lost. So how do I move a gas? So I just do like a Pythonic thing for particle in the list of particles in my gas, move each of them. So the code, it's almost exactly what you would write in Python, except you'd put g.move instead of particle.move. Right? So it does work. So that is the end. So there's this, that's basically the end of this first notebook. So that's sort of supposed to be covering the basics of the Julia syntax. Any questions? Is it clear? Is it? Yeah. That's a good question. Is there any equivalent to doc strings in Julia? That's sort of in the works as well. How do you document packages? How do you document functions? So, so when you do this sort of help of something, help of dot, it prints out some information, right? So where does that information come from? That's a good question. I'm not actually quite sure where it comes from. I'm not sure if it comes, if there's some, I'm not sure where it comes from. That's a good question. Oh, for goodness sake. So it's not written in there, right? That's what I was wanting to check. So I don't know exactly where it's written, that documentation, I'm afraid. Okay. But yeah, that is something obviously that everybody is thinking about. Yeah, so there must be some. There's a doc. Yeah, there's a doc subdirectory in the Julia thing with REST files. I guess something is in there probably. Okay, sorry about that. Okay, so next one. Graphics. So everybody wants to do graphics and packages, right? So, oh dear. Oh dear. Okay, that didn't quite work. I have a problem managing all my tabs. Oh, I think I changed the name of the notebook and, of course, didn't update the link. So how do packages work in Julia? So what's a package? It's just like a module or a set of modules that define new functionality, that define new types and new methods. And so as examples of interesting packages, let's look at some graphics packages, because everybody has to draw things. So the first one that we can look at is the PyPlot. As I said, it's an interface, a Julian interface to the matplotlib Python plotting package, written by Stephen Johnson, who's well known in this community. And it's a very, it's sort of pretty complete wrapper around matplotlib. So how are we going to install that on our system? From within Julia, we're going to add this package with package.add, right, with capital P. So if you haven't done that already, and that's something I put on the instructions, then you just sort of execute it. You can even do it from within iJulia or from within the REPL. And so what it's going to do is go and look to see if you have it installed, look to see what the version is in this thing called metadata, which is the list of all the data about the packages in Julia that there are. Compare the two, see if you need to update, see if you have it installed, and install it if you don't have it, right? And so they're all GitHub, Git repos, Git repositories, the packages, and so it'll download them all, as I said, into the .julia directory in your home directory. So in PyPlot, there's just a load of stuff, which is basically Julia code. There it is. So the whole wrapper is in this pyplot.jl thing, and there's the code, and it's not even that long. Because it uses a lot of metaprogramming to do exactly this sort of... So there's a lot of boilerplate code, which is just wrapping Python functions in matplotlib with a Julia version. And so that's, you don't want to be doing that by hand, and that's what the metaprogramming allows you to do. Okay, so then that just puts it, that just gets it from the interwebs and sticks it on my computer. So now I have to actually make it accessible to my code using PyPlot. So as I said, that grabs all the names that are in the PyPlot package and makes them available in my current namespace. As like from PyPlot import all, import asterisk in Python. So it's probably maybe not such a good idea to do it, but sort of people tend to do that apparently. So that makes available all the nice matplotlib functionality. So I can just define Julia variables. X is ran 10 and Y is ran 10. They're Julia variables. And I'll send them to this Julia function plot, which is going to pass those off to the plut.plot thing in matplotlib. And all the interfaces just there. And so I get back a matplotlib plot. So it's really, really an impressive piece of work. Right, exactly, yeah. So if you don't have matplotlib, you get an error at some point in the process, which happened to me the other day, and I never managed to fix it until I installed Anaconda. Okay. So what is P? So then I put P equals plot to say, to see what is this, the type of this object that I'm getting back. And the answer is it's an array of Pi objects. So what is a Pi object? It's a Julia type that wraps a Pi object star, which is the C pointer to a Python object. So we'll see a bit more of that later. So this is using the PyCall interface between Julia and Python that I'll talk about a bit later. But it just works. So you don't have to worry about any of that to just use matplotlib. So here's another example where I just changed the figure size. Right, so here I did the alternative, which is import pyplot, so that just everything's in the pyplot namespace, and I just do pyplot dot something instead. So yeah, again, pyplot is a Julia object, right? A Julia name. Okay. So I like this example of random matrices, but so I'm doing exactly the same thing. I'm just going to use the hist function in matplotlib to do a histogram, and I'm using this pyplot interface. So everything you know from matplotlib is immediately applicable, and you can save the figure with savefig because I've imported all the names, or with pyplot.savefig. And I've got tab completion and everything because I'm in IPython or iJulia. Okay, is that clear? Questions? So that's all I'm going to say about pyplot because that's all you need to know, really. Okay, so I mean, there are some subtleties to doing complicated things with Matplotlib. So another interesting plotting library is Gadfly. So we're going to see that that really takes a long time to import because it's pretty complicated code, and it's compiling it sort of in the moment. So that's that's what's going to have to change soon, hopefully, to pre-compile certain packages that you use a lot. Actually, you can already do it. So you have to sort of list the package in your sysimg sysimage thing in base Julia and recompile, and it should work, something like that. At least that's what I was told the other day. I haven't tried it, so. So there's this thing called sysimg.julia. And somewhere, yeah, so here, all of these are the Julia files that are being loaded sort of when the system starts up. And they're being pre-compiled. So when you compile Julia from source, you'll see that it sort of goes through these, it seems to be looping through this list of files several times, and that's sort of doing this compilation step somehow. So if you add there include, so include is just sort of copy the contents of the file as if you were typing it in the terminal. So that's sort of a previous thing to import and using. It's just literally dump the code from that file straight into the terminal. And if you add there include the package name, apparently most of the packages should be able to be precompiled in that way. Not sure. Yeah, it sort of caches some version of the compiled thing, yeah. Not sure exactly which level of code it is. Okay. So what's this Gadfly thing about? So it's something like ggplot in R. It's a grammar of graphics idea. So it's a completely different approach to plotting than Matplotlib, sort of a modern point of view or something. And this implementation is really very nice. So it's not working because it's trying to overwrite the word plot that already exists, and it's giving me a warning that I've already got a plot from PyPlot, so it's not going to import the Gadfly one. So let's restart the kernel, reload Gadfly. Several minutes later, we can do something. So the basic plot is just going to, basic plot command works in the same way, apparently, same way. Oh, come on. Yeah, this is kind of a long time, right? So hopefully they'll get round to that step soon. So they is, a sort of group of core developers, but of course anybody can contribute. So anybody who is desperate to have Gadfly start up fast just needs to get their hands dirty and code up some stuff, and it should work.
People were complaining about Matplotlib for a time.
Right. Yeah. So the kind of plot that Gadfly gives is kind of a different aesthetic. Oh, come on. Really? Yeah, but it shouldn't be this slow, I don't think. I mean, there's some, right. Yeah, I mean, my computer's getting hot as well. Okay, so it gives this nice plot, and if I mouse over it, I see up here, the grid changes color. So this is using nice JavaScript and stuff, right? And I can zoom in and out interactively inside the browser. So this is the kind of thing that Matplotlib will soon be able to do with IPython Notebook, but this is already, it's already got it, right? And I can pan around, right? And I don't think you can sort of select things like Jake's nice library yet. Okay. So so I can, just by changing the word, just by adding the word, so automatically it gives me dots. By adding the word or the phrase geom.line, so geom for geometry, and line is sort of inside the geometry object, I get this. Well, why do I even run the thing? Right? I get this instead. So I've replaced them by lines, and if I put both of them, then I get both points and lines, and it sort of does this neat trick where it has a little bit of space around the point. Okay, so if I instead do random, have I got random points? No. So let me put in here random points. What would we expect? Well, we'd expect a sort of random mess of joining 10 points at random, but we don't actually get that. We get this, because it turns out that by default it orders the data in the x direction. So to avoid that, we put an argument here, preserve order equals false. True equals true. No, true with a small t because we're not in Python. And then I get what I expect. So, yeah, so it's quite different if you're used to sort of matplotlib kind of imperative style. It's much more declarative style. It's difficult to get your head around, actually. So then you can add labels on the x-axis. So there's this thing called guide, which is sort of all the information about the plot. And you can do different layers that I didn't manage to get to work properly. So I can sort of put colors that I didn't quite understand how to do that. And then you can have sort of different things going on the plot. And there's, Daniel Jones gave an amazing demonstration in JuliaCon, and once the videos are up, you should really have a look. It can do some amazing stuff. And then you can save it to PDFs and other formats. So there are some cool examples using some other packages. So there's one called data frames, which is like the pandas package in Python. And there's R datasets, which is a collection of datasets, like standard datasets that people use in R as examples to work on. So I've got them installed already. And Gadfly can just, so what are those? Oh dear. Thanks. Yeah, didn't execute the using R datasets. So it's sort of very similar to pandas, gives you this nice table. So what kind of type is that? It's a data frame. And then Gadfly knows what to do with data frame. So the data frame has several columns, and I can specify which data from which column I want on the x-axis, which data I want on the y-axis, and draw it with points. And there it is. And there's some other data here from a different data set called, which is some stuff about cars. And I can choose what I want on the x-axis, and then I can facet the data, I think that's the right word, by color, according to some other part of the data set language, and it just sort of does the right thing if I import the right data set. There it is. So it gets some really pretty beautiful plots, and it's just a completely different way to think about how to graph stuff. So the documentation is still in the works, let's say. So that's why I'm suggesting to look at his video. So this is the stuff I was saying about how to use modules. So all of these packages are really modules. So I guess we already had a look at that. So if I go into the Gadfly directory, then it needs all of these modules. So require is yet another one of these things of telling you how to import stuff. So it sort of checks to see if it exists. And to be honest, I still haven't quite got the differences straight in my head. And then it imports all of these things. And so it imports all these things from base that it's going to modify. Then it exports all these things, which are what I'm going to be able to see from outside the module when I do using. If I do import in the module name, then I can actually access anything that's defined in the module, even if it's not explicitly exported. But export is what I'll see if I do using. So a package is just sort of a module or several modules. Okay, any questions? So, the exercise is take your favorite data set and try and get Gadfly to do something useful with it. Yeah.
Is anybody else getting unknown package?
Yeah, that's right. Thanks.
So you just mentioned packages and namespaces, but I haven't seen any examples where you show how you avoid name collisions. Types or functions, how does that work? I mean, what if two people define the same type of
Right.
their modules?
Right,
How
just,
do you do it?
yeah, I just had an example of that, no? With pyplot.plot, and yeah, so I mean, the way to avoid that, one way to avoid that would be to import pyplot, import gadfly, and then you have pyplot.plot and gadfly.plot.
Okay, so you can do that.
Yeah.
And you can do that for the types as well?
Yeah, I think so. No, you can just put plot. You can just put plut equals pyplot, right? I guess. Let's try. So so import it first. So let's import pyplot. So because I restarted, right? So I'm going to put plut equals pyplot. So I don't know if you can do import pyplot as PLT. Actually, that's a good question. Yeah, I think my computer's sort of too slow. Yeah. Plut.plot is the function plot in the pyplot module now. That's a nice idea. Okay. More questions? So what's next? So I wanted to do a small example of defining a new type that's a bit more complicated than the vector one, or sort of similar idea. So, so various languages like Pascal and Fortran have arrays where you can start from -3 as the first index, and that's sometimes useful in a scientific context. So how would you do that in Julia? So that doesn't exist, right? I mean, arrays have to start with the element number 1. So the question is, can we even define an array that has that has that kind of idea? If you want to do that for some reason, how would you do that without cheating? That's why I put a big blank box there. What would you do? So I want to define a new type, which is called, for example, indexed array, and I want it to be just an array, but the indexing can start from some other value, right? So when I construct the array, what do I want to give it? What do I want to give to the object? Is it clear what the question is? So I want to do some kind of array, indexed array. So I want something like A equals indexed array of 3, 4, 5, but where it starts with the index -7, right? So I want A square brackets -7 to be the first element that I can access, -7, -6, -5, and then there are no more elements, right? Is that clear? So I want to be able to say A -7. So at the moment I can't do that. But I could define a new type called indexed array that actually does that, right? If I wanted. Is that clear? Questions? So, so I want an object that takes some data and takes this number and sort of just does what it has to do. So just like in Python, there's going to be some function, it's called getIndex, that returns the right. That does the square brackets functionality. So square brackets is another name for getIndex or setIndex. So I've just got to define this type and do sort of redefine all the operations that exist on an array. So that's So that's where some kind of inheritance would be useful. But there are sort of ways of, I think there are sort of ways of inheriting some of the stuff. Some of the functionality. So let's have a look. So we're going to define the type, and it's going to have the data, which is, I'm just going to think of in one dimension. So it's going to have some data, which I can just think of as an array of a vector of float 64s, and it's going to have the sort of this index where it starts off the indexing, which is going to be some kind of integer. And then what I have to do is define all the functions that give my array functionality. So for example, get index, when I give it one of these indexed arrays, and a number should give me back, the right element in the data set, right? So as I'm going to have a.data, and I'm going to choose some element from that data. So I just define this reindex function, which I had to think about it quite a lot for some reason. Exactly what is the formula to go from your number I to the standard Julia array, which is indexed starting at 1, right? So it's just I minus the low thing plus 1. So it would be I minus the lowest index if it started at 0 in Julia, but it starts at 1, and that's why they're plus 1. So I just have to sort of re-implement, but it's not even that much work, right? Because they're just these one-line functions. I have to re-implement all the functionality of these functions that act on arrays to give me the indexing functionality and other functionality of arrays. Is that clear? So this is, again, using multiple dispatch. So if I define these things, and then I define an indexed array with the data 3, 4, 5, starting at -3, now I can access the element number -3, the element number -2, the element number -1, and I can't access the element number 0. It gives me a bounds error because it's trying to access something that's outside the original, outside the Julia array. Is that clear? Any questions? So I've got the basic functionality there, but now I can't. So this is kind of like supposed to be a sort of step-by-step exploration of how would I go about doing this, defining this kind of new type. So now the problem is I can't do v of -1 equals 10. I can't change it because it says no method set index bang of an indexed array with 2 integers. So when I'm trying to change something inside an array, it's going to call this function set index, and it's got a bang because it's going to modify the array. So I actually have to define that myself again. So here it is. So I again re-index the thing in the right way, and I define it, and then I can set the element in the array, and the array does indeed change its first element. So then what's the next thing I could want to do? I could want to iterate over the array. And I can't do that because it says no method start of an indexed array. So it turns out that iteration in Julia is defined by by 3 methods, start, next, and done. So what's the best way to understand? So yeah, I was looking in the manual, how do I define start? I couldn't find it. You look on Google and you get a mess. So what's the best way to know how to go about implementing this functionality? I have to define these functions for my new type, right? Yeah, look at the source code. So methods, so it's telling me that I need a start things, right? So let's look at methods for start and choose one that's closest. So abstract array is a sort of abstract version of an array. And there's the link, so I'm just going to go in there, hope that it works. Oh, come on. And there it is, iteration support for arrays as ranges. So I'm just going to copy that. So I already copied it, so I'm going to copy that, stick it in my source code, here it is, and then modify it in the way that I need to modify it. So what is this? It's like it's sort of a simple iterator protocol. So start tells me which is the first thing that I'm supposed to return, which is the first element, or where do I start off my iteration. Then next takes the current value, which is this 1, returns the value that's at that point, and then returns the next one along as a tuple. And done is a condition that tells me when I'm finished. So to extend those, I have to import them from base, and then I just define them in the right way, which I also had to think about. So you start at the low index, because then next is going to return A evaluated at that point. So it's already using the get index that we defined to do the right thing when you put in -3, and then it just advances 1. And the done method is a bit more complicated. You have to work out, again, do the calculation of when you're out of the bounds. So once you've done all of that, you can define your vector, and then you can not do anything. Oh dear. It was working before. Oh, I didn't import base. Yeah, so there we go. Yeah.
So it looks like you could also make an array that's indexed only on even numbers.
Yeah. Yeah, you could do sort of nice things, yeah. Yeah, so this was a particularly simple example, but I think, in some functionality that I have missed, actually, in my scientific work, to be able to just index from some other place without having to, so somebody has to implement it, but then even if I implement it, then I just, in my actual production code, I just do what I want to write instead of having to be writing all these re-indexing functions all over the place in a complicated way, right? So I think it's just a nice example. It isn't necessarily really that interesting per se as something that should be in base Julia or anything, but it's something that you might want to do in your personal code just to clean your sort of main code base. And it's a good example of how multiple dispatch works with just implementing these new types, and a sort of step by step, it tells you what you need to implement for each bit of functionality, right? So it's pretty nice. Okay, questions?
So would you have to, if you wanted to be able to add these new index arrays, would that work automatically? Do you have to re-implement add?
Yeah, you have to re-implement. Yeah, you have to re-implement add. Yeah. But it's a one-liner, right? But yeah, it's annoying. I mean, so probably you could do some clever metaprogramming thing to do it automatically in some way. Okay. More questions? Okay, so let's talk a bit about performance. How do I get good performance in Julia? So there's this performance tip section of the manual with a lot of stuff. Some of it's quite advanced, so I just picked out the couple of sort of main things that always crop up on the mailing list. So whenever you're checking performance, you're checking timings, because of this JIT compilation stage, you should always run the function once without looking at its time, without timing it, and then time it. So because the first time you got the compilation time in there, which you're not interested in. So so that's the first tip. And so how do you time things in Julia? We haven't seen that yet. So oh yeah, we did see that. Well, I showed it. Okay. So you can use this at time macro. So you just put some code in there, and it'll time it. So again, that first time there was this sort of delay, which there shouldn't be calculating sine 10. So let's run it again. So it goes down from 0.003 seconds to 6 times 10 to the minus 6 seconds. So we shouldn't trust these tiny numbers. But you can see that there was this effect of the compilation phase. So one of the two main tips is that we should not use global variables in Julia. So we can. So everything I've been doing is just defining a sort of global variable A that then exists throughout the whole program, or throughout the whole notebook. So we should just wrap everything in functions, And if you need to use something that would, you would use as a global variable, you just pass it into the function as an argument and return it from the function if you modified it. And why is that? Because there's some technical thing that makes it really difficult to do type inference on global variables, and we're about to see that type inference is really important for performance. So that's to do with this type stability thing. What's that? So an algorithm, as I mentioned, in an algorithm, you should you should not have any variable that changes type during the process, right? So this is why Python can be slow for for loops, and why in Python you end up defining the types of things. So here's a simple example that I learned at JuliaCon. I mean, it's a nice, really simple example. So this was Leah Hansen, who's one of the Julia people. So let's define two sum functions which haven't got any syntax highlighting for some reason. Did I? Yeah. So the first one, so it's going to take an integer n, and we're going to define this thing total, starts at 0, and we're just going to sum up half of all the integers from 1 to n. And then sum2 does exactly the same thing. So what's the difference? Yeah, here total starts as an integer, and then as soon as it hits this 1, when I'm dividing it by 2, it's going to be a floating point, and so I'm summing an integer and a floating point, and it's going to be changing the type of total from an integer to a floating point. And then here, it starts off as a floating point, float 64, and it's always a float 64. So this sounds like a really trivial change. So let's see. So just check that they do actually give the same answer. So let's, oh yeah, and then that's also compiling them, right? So I'm running it for the first time with some small argument, so they get compiled with the correct types. And so now I can go along and time them. So here's 10 million. I'm going to sum up to 10 million. The first version with the type instability where it was changing type has 0.65 seconds, and the other one 0.039. So there's a factor of 15 just because of that changing that 0 to a 0.0. Yikes. Yeah, and also, look at this this nonsense going on, right? So when we have just the floating point, it's allocating 96 bytes, and when we have the type instability, it's allocating a lot of memory. Right, so that doesn't mean that it's reserving 320 megabytes. I mean that it's using 320 megabytes. It means it allocates a bit, it frees it. It allocated it, it frees it. Allocated it, it frees it. And it's actually 36% of the time was in garbage collection. This is GC as garbage collection, so it has automatic garbage collection. You can turn it off, you can turn it, but by default it's on. And so, so that's exactly what's happening. It's allocating and freeing all the time because of this type instability. So it's kind of surprising, right? Yeah. Yeah. Exactly. So that's nasty, right? So you really have to be really careful about this this thing, and if you're allocating that much memory for such a simple thing, that should be a warning that there's something weird going on, and that you should go in and look at it in more detail. So, yeah, I mean, there's sort of every week there's sort of a new step on that kind of direction. So there's a recent package called lint.jl, which does that. There's another one, typecheck.jl. Yeah. So let me write those down. Okay, so one useful feature to do this type stability is that there are functions 0 and 1. So what do these do? So they take a number that's of a certain type, and they return the 0 of that type, right? So x equals 1, 0 of x returns an integer 0. If I put y equals 0.5, 0 of y, it returns floating point 0. If I put x equals big float of something, then 1 of x returns the 1, which is a big float 1, with that same precision. So that's useful for type stability stuff in the sense that you can guarantee that you're getting something of the same type that you're then going to manipulate later. So if you're sort of brave, you can explore really what's going on in this code. So what happens when this Julia code gets turned into something more closer to the machine? So there are 4 functions that do this. So code lowered, I pass the title, the name of the function, and the type signature. So that means it's a tuple with the types of all the arguments. And if there's just one argument, then I have to do this, tuple with a comma and nothing else. And then it actually gives me a sort of splurge of stuff, which is what's called the lowered version of the code, where it's reducing the code to a sort of simpler version. It's turning all the variable names into these sort of weird, unique variable names. And, okay, that's the sort of, okay. And it returns this thing with a colon that I'm going to talk about a bit, which is Julia code expression. So this is Julia code in a Julia object. Then I can do the same thing with sum2, and if you compare them, there should be a difference because of this type instability. And I think you can't see it in this level, but if you do code types, then it actually now annotates every single variable with its type. And so in sum1, there is this union. So what is union? It's a special type that can be either an int64 or a float64. And that is what is causing all the grief. And so all these box things is where it's wrapping the raw number inside a thing with a pointer to the raw number. And that's what's happening there. And if I do the same thing with sum2, then that doesn't happen anymore. And so somehow the code is simpler. And it's not going to generate so much nonsense. And then I can go down a level to this LLVM, which is the JIT compiler that Julia uses and that Number uses and that everybody uses these days. And that's I have no idea what's going on here. And then you can actually get down to the actual machine, actual assembler that Julia produces, well, the LLVM produces from this code. Right? And there it is. I have even less idea. Okay. But I guess there are people here who know what's going on here. But it's telling me which bit of the source code these things are coming from. So it's all pretty neat. You can really sort of drill down to the metal and see what's going on. It's pretty impressive. Okay, so how do I profile my code? So simple profiling with the time, complicated profiling with @profile. Oh, not complicated. I mean more. So let's try that. @profile sum1. Sum1 of 10 million. So it's going to run the code. Oh dear. Okay, so let me define a function that just calls sum1. Maybe that's going to help. Profile f of 10 million. No, so I've forgotten how to use profile apparently. So I thought you just did that and it sort of spits out a profile of, it's doing a sampling of every millisecond or something. It checks which bit of the function or which function it's in or which line of the code it's in and spits out a list of those the counts of which line of the function it's in, so you can actually just see this big number where it's spending all its time. So I did that with some of my code that I was saying that I replaced with this fixed size array, and that's where I saw that the array arithmetic was really killing me, and so I replaced it with a fixed size array, but I've forgotten how to do it apparently. Sorry. And there's this package called Profile View, which does a graphical version of the profiling. Okay, so we have questions. So we still have 2 kind of big topics left. Metaprogramming and interoperability. Operability. So maybe I'll talk about interoperability first. interop. That's why, now I understand why people call it interop. Okay, so how do you call Python from Julia? So, if we want to use Python, if we don't have a package in Julia, for example, for natural language processing, and we have NLTK, that's the natural language processing toolkit, apparently, want to call it from Julia. So there's this really nice package using PyCall that makes it completely trivial to do that. So somebody did a lot of work, Stephen Johnson, again, to make that happen, but we can just use it in a very simple way. So we do @PyImport_math. So again, this @PyImport is a macro, and that imports the Python math library, and makes it accessible from Julia with the name math. So math.sign is accessing the sign function in this Python math library. 0.3 times the math, again, the pi from the Python math library, and then we're subtracting sign. This is the Julia sign of 0.3 times the Julia version of pi. And happily, it gives something that's close to 0. So this is like the machine epsilon. So maybe that's a bit surprising that they actually give different answers. Slightly worrying, maybe. Don't know what's going on there. Okay, so we can import more complicated packages. So PyImport numpy.random, and we can give it a name. Actually, we have to give it a name as np_random, and then I can access things from functions from, numpy. So this numpy function returns a numpy array, and that numpy array is automatically converted to a Julia array, just behind the scenes without me even thinking about it. So it's actually doing, so if I send a Julia array to numpy, then it's not copied, it's just sort of passed along. If I get back a Python array and convert it to a Julia array, by default it is copied. So that's maybe a problem. So there's a way of getting around that with PyArray that I haven't used. So we can do more complicated things. So here's how we can define an anonymous function in Julia. X minus greater than, so like arrow, x arrow cos x minus x. This is an example from the PyCall README. I'm going to give that the name objective. It's an objective function I want to optimize. And it's just a standard Julia function now. So I can call it with the value 3, and it returns the value of this function when x is 3. And we can pass this straight to the Python SciPy.optimize module. So we'll import the Python SciPy.optimize module, we'll give it a name, and then we'll call the Newton method to solve, to find a 0 of this function. Which function? The Julia function objective. And this is 1 is the starting value. I don't think we can get the help. No. Oh, right, so I should have to do the import. No, we can't get the help so easily. But, so we're sending this Julia function. No, it finishes at 5. Started at 1, yeah. We're sending the objective function to this Newton method in the SciPy optimized package, and it returns the number. I mean, it's just amazing. So here's a more complicated example. SciPy integrate to solve a differential equation. So here's the function that I want to integrate. Yeah, so it's x dot equals minus x. Well, whatever. So that's the Julia function. Here's a Julia array of times when I want the solution. And I'm going to start in the initial condition 1 and send to the ODE int function, this Julia function, this Julia number 1 and the Julia array. Send all of that straight to ODE int, with some conversion that's going on behind the scenes. So I have to do all this stuff. So all of these things are converted, in some really neat way to Python objects. And then once I've solved it and I've imported PyPlot, I can just use PyPlot from Julia to plot the solution. just kind of surprising. I'm sorry? No, I'm calling this. So this SciPy.integrate is the Python module, SciPy.integrate. So SciPy, so I'm calling it integrate, and then I'm calling the ODE int function, which is in the SciPy module, written in Python, which calls the Fortran library, returns a Python array object, and that Python array object gets converted to a Julia array called solution. Is that clear? And so then I'm calling this plot from pyplot, so I'm sending it this now Julia array T, the Julia array solution. It sends those into, converts those into Python objects and sends them to matplotlib and returns the matplotlib object back to me in Julia. Yeah.
Is there much time required in conversion between the Python
No, so from Julia to Python, it's just a wrapper around the same data. But from Python to Julia, by default, it makes a copy. So yeah, that can be a problem. I'm sorry? Yeah. But so there's a way to avoid making a copy, but you have to go to the lower level in PyCall. Okay, so there's one difference. You can't just write it as if it were Python, because in Python you have this syntax that we've been talking about that we don't have in Julia, which is this obj. If I have an object obj and a function b of it, then in Python I would just write obj.b and call it, and that's what I can't do in Julia. So I can't even do obj.a if a is a property, because dot is only currently in Julia. You can only use it with. You can't sort of override it. So there's a strange syntax that they had to use. So we're going to use obj with these brackets and then put this colon a, that again is this thing. Well, it means like the symbol a. So I'm about to talk about that. So here's an example. So there's this. So on the lower level, what is PyCall actually doing? Is setting up sort of references to Python objects from Julia. So the basic way of doing that is this PyObject thing. So what is PyObject of 3? 3 is a Julia object, and it's returning a reference to a Python version of that Julia object. So let's do that with a more interesting object. X equals a Julia array. And now I'm going to convert that Julia array X into a Python object XX. So it's a Python object that's like a version of this Julia array. So that is a thing of type PyObject. And so it's called XX. So what is there inside XX? So I can look at all of the names, all of the things, all of the variables that exist inside this object. And there's only one, and it's called O. So if I look at xx.o, what is it? It's a pointer to a PyObject. So it's this like really low-level thing. And then how can I access, so it's referencing a Python ND array. So a Python ND array has lots of properties that I want to be able to access, and this is how I have to do it. So I would want to do xx.shape, but that doesn't exist, because XX is really a Julia object. So I use this strange syntax, XX, square brackets, colon shape, and that is the equivalent of xx.shape, and it gives me the shape of the Python object. Right? So that's sort of a bit of what's going on. There's, of course, much more going on that you have to go and read about in the PyCall documentation and, of course, the source code. So call your favorite, Python. So exercise, everybody has their favorite Python package. Just use it from Julia. I don't know, scikit-learn, whatever you want, right? So it should be just trivial with this pi import thing. You can really just do everything straight from Julia. Yeah.
Have functions first class type.
Mm-hmm.
So you usually make a type with function type.
Right.
So then you can't have this syntax before. Having like object dot f.
Oh. Oh, I see. Good question. So you mean like type?
The tricky part would be in the constructor you have to somehow reference the object. This maybe is actually really like when you have to reference something. So like this works. I just tried this. But it's a generic function, right? And you want to
Right. Yeah. So let me create an actual function. So hello of x equals x squared, and now I want f. I want to pass it hello, and I want to call that something like myfunc. And so now myfunc, what is it? Yeah. So myfunc.f is the function hello. So I can indeed call myfunc.f and put 3, and it'll give me 9. Yeah.
So what I tried to do here was, in addition to putting an f in there, just put some kind of other variable that you want to play with.
Right.
And the trick now is that you have to pass it to the function. Like you want to somehow achieve a closure over the other variable in your type, right? And then suddenly you have like normal objects.
Okay.
It sounds weird, right? So
Yeah.
in 23 here, in addition to f, think like x.
Yeah, of course I would have to, I can't modify the type, so I'll restart the kernel, yeah. Yeah. So x is a float 64. So now,
And now when you go to define my function,
oh, so I have to, and 3.5. Yeah.
and so now when you call hello, you also have to pass like myfunc.f, but then for your argument, you also need to say like myfunc.x. But I'm wondering, is there a way to get around, so to make sure that you're grabbing the right x from
Right, yeah, so the answer would be use a macro. So let's look at macros. Thank you, good segue. Metaprogramming. Yeah, good question. Very nice. Okay, so what on earth is metaprogramming? That was my question until a few days ago when I finally grokked it. So yeah, there's something meta going on. So when we talk about meta stuff, it means sort of one level up in some philosophical way, right? So we're going to talk about Julia code from within Julia. So this is called, sometimes they say treating code as data, which doesn't seem to help me understand it. So we're just going to have objects that represent Julia code, and those are objects that live in Julia. So, okay, the basic objects to do this are these unevaluated symbols. So they're written with this colon. Colon A is the symbol A. So what is the type of that thing? It's a symbol. So it's a piece of Julia code. So we can evaluate it like we would in Python if it were a string. But it's not defined yet. So I can define A, and then if I evaluate A, then I get 3. So so I mean in Python you have to do everything with strings. And in Julia instead of strings, we're going to use these bits of code. Right? So this comes from Lisp, so if you know Lisp, you're happy. If you don't know Lisp, you're confused, probably. So everything is a symbol. So we have the symbol plus, the symbol sign, and they're all symbols. And then we're going to combine symbols into expressions. So X is going to be an expression, which is the expression A plus B. The Julia expression A plus B, like the bit of code A plus B I'm going to give it a name, x. And it's, what type is it? It's an expression. And so x, ex, x is a Julia object, right? Who is x? It's the code a plus b, the expression a plus b, the unevaluated expression a plus b. So again, I can evaluate it. If b has a value now as well, then I can evaluate this expression, and it's going to add a and b and give me 10. But since it's a Julia object, I can introspect, I can find out information about it. So what things does x have inside? What variables are in this type? Sorry. So what things are in there? There's a thing called, so what is x? It's an array of symbols. No, that's not true. No. So x has inside it three things, which are symbols. So the head is call. So expression, so what is the structure of expression? It's a call. What am I calling? I'm calling the args. So I'm calling plus on A and B. Again, type is, I'm not sure what it is. So that's the structure of an expression is call plus AB. So it's like a very Lispy thing. And so when I have a more complicated expression, I get a nested structure. So if I have this new expression, which is a sine 3a plus 2b squared, then I can ask what are its arguments. So it's got this hierarchical structure. It's sine and then the expression 3a plus 2b squared. So then I can ask what are the arguments of that second bit. Or what is the type of that second bit? It is an expression, so it has arguments as well. And so then I can see this hierarchical structure of this code expression, which is stored in this Julia variable, and I can access bits of it. Is that clear? So this is kind of hard to get your head around. At least I found it hard to get my head around. So for longer bits of code, instead of this colon bracket syntax, we can use quote end syntax. So quote end is exactly the same as colon brackets. So just wrapping all this bit and making it an expression. But it prints it out in a different way just to be contrary. So blocks in Julia are generically, I can make like a generic block of code with begin and end, and then I just put the other stuff inside. Okay. And, I can sort of get other representations, like more detailed representations, so I can get the whole expression dumped out, or sort of spun out into a more complicated thing with colons all over the place. So this is sort of a different representation where we now see the indented, bit where we're calling a function of the result of calling another function. We can also dump that expression. So dump is a generic Julia thing to get the structure of an internal expression. Oh yeah, so we're now in the more internal side, right? So more oriented towards developers. But it is useful to see this, even if you're just sort of a user, because when you explore code, you're going to be seeing these at things and macros all over the place. You have to know what's going on a bit. So it just expands it in a sort of more complicated, indented hierarchy thing. So that's the object that in Julia we can use to talk about Julia code. And now we're going to actually use that. Now that we can talk about Julia code from within Julia, we can write Julia code from within Julia. So we can program, programmatically write a program. So that's why it's called meta-programming. So we're programming a program. So why would we want to do that? It sounds, tricky. So to eliminate boilerplate code, as we've discussed, to generate complex code that would be difficult to do by hand, to unroll loops for efficiency, and to inline code for efficiency, and probably other reasons as well. So these at things that we've been seeing are these macros. So what is a macro? It takes an expression, these kind of Julia expressions that we've just been seeing, and does something to it, manipulates it to produce a new expression. So that, in that sense, it's a super function, but it's a function acting on expressions and giving me expressions back. So let's look at a really trivial example of defining a macro. It's just going to take some code and just copy it twice. Exactly the same bit of code twice. So we write that like this. Macro, we give the name of the macro. So we're defining the @duplicate macro. It takes this argument, which is a Julia expression, and it creates another expression. So how do I do that? I could either do it with colon parentheses or with this quote end syntax. And so inside that stuff, what do I need? I need a copy of the original code. So I need to interpolate, need to push in the original code that I had, and I want to do it twice. And so I use the same $ syntax as we use in strings, and interpolate that twice. So I'm just copying the code twice. So it looks like something I could just do with a for loop or whatever, just call some function twice. But this is sort of subtly different. It's actually duplicating the code and spitting out twice the amount of code. And so the macro incantation, when I call the macro, it's going to actually replace that @macro blah, blah, blah bit of code by whatever the macro spits out. It's going to replace that before it does any of the other steps in this compilation that we just saw. So let's look at that in action. So what's the result of doing @duplicate print line sign 10? It just prints sign 10 twice. But if I want to really understand what's going on, I just stick all of that in an expression. So if I evaluate that expression, I get the same thing again. But now I can actually expand the macro and see what it's doing. So that macro is going to be replaced as the first step in the sort of code generation cycle in Julia by this bit of code. So it's literally copied the code twice. It's expanded that bit of code twice right there in the sort of abstract syntax tree, as they call it. So this is going to be part of my program, and it's just literally now I have a program that instead of that macro call has this same line twice. Is that clear? So here's a more complicated example. What happens when I call time sign 10? It sticks all of this code in my syntax tree. It sticks this code in what's going to be compiled. So this is how it calculates the time that it takes to run this function. It calculates, how many bytes the garbage collector has used, the time in nanoseconds, the garbage collector time in nanoseconds. It does the call, and then it calculates them all again and just prints out the differences between them. So that code just gets expanded whoosh, to all of that stuff. And that's what's generally happening with all these macros. So we can see that it's pretty. You can see that it might be able to be used in a very powerful way. So I'm really generating code from sort of more simple expressions. So an exercise. Define a macro @until that does an until loop. So I've often wanted in code to write, until something is true, do something, right? And no language that I know has an until loop. They all have while loops, so you always have to think about the negation of the thing that you want to do the until. So now you can actually change the syntax of Julia, or like add to the syntax, or make some new syntax, which is @until, which really does what I want. It does an until loop. And it's actually pretty easy to do, so have a go. So you're going to have to define a macro, so you're going to use this macro end. No? So we're going to put macro until. It's going to take some argument or something, and then you sort of put the stuff in there to do this until loop. You mean, can I define macros in a module? Yeah. Yeah. Yep. Yep. So actually, I think I've got an example of that coming up. Yeah. but it's really useful to try and do this exercise. So it starts to get you thinking about what's going on. Right, so what is until going to do? It's going to take some piece of code, and you want to actually, well, so what is the idea of this until macro going to be? What do I want it to do? So I want until a condition, do something, right? So I'm going to take that, nice way for me of thinking about it and turn it into something that Julia understands, which is going to be what? A while loop. So I have to convert my thing into the right thing for a while, to basically convert it into the while loop that I don't want to write, because I have to do an extra thinking step that I don't want to do, right? Is that clear? So it's literally going to take my sort of silly until loop, and it's going to replace that until loop with the code for the equivalent while loop. Right? It's kind of a head twisting thing. So have a go. So here's the, template that we're going to follow, right? Does somebody know a language with an until loop? No? Oh. Okay.
Is it until or unless?
Okay. I don't think I've ever written until in a piece of code until today. Sorry? Okay. Right, okay, so I'm just ignorant. That's clear. Yeah, quite. But the point is, I don't have to know any of those weird languages. I just use Julia, right? And invent my own language. So I'm not suggesting that it's a good idea necessarily to write an until macro, right? It's just a very simple example. It's not actually that simple. I mean, it's sort of, introductory example, let's say. So it's going to look like this, right? So I'm going to have the macro until with the expression, there's the argument to the until. So what do I want to do? Start a while somehow, yeah?
Okay, why don't we incite the quote?
So the quote is, what is the quote doing? Yeah, right. So the quote is like the colon with the parentheses. So the point is that a macro takes an expression and has to return an expression, a Julia expression. So the Julia expression, I can either write it with colon parentheses, or I can write it with quote. So that's just a way of saying I'm going to return something that's a Julia expression. So the stuff that I'm writing, I want you to convert it into a Julia expression. I'm writing a Julia expression. That's what the quote does. So the macro always has to have that quote. Or colon parentheses. So if you prefer, we can do it with colon parentheses. Maybe it's clearer. So what am I going to do here? What's the not operator? Good question. So the heritage of Julia is C, or one of the many heritages is C. So it's not like that, with a bang. And then I want what? do stuff, yeah. So I think if I try and do it like this, it's not going to work, right? So it's sort of, it's not able to parse that. I need an end for the while, yeah. What else do I need? Yeah, the do stuff part. So what I was trying to do was just have something that replaced the at until something with while not something. But apparently you can't do that. You really have to have a whole bit of code, not just, can't sort of do these mini replacements of, right? You have to replace a whole sort of block of code. So actually what I need is the do something is going to be another argument to the macro. At least this is how I did it. So expression 1, expression 2, expression 1 is going to be the condition. So while I'm not, while I don't have that condition satisfied, then do expression 2. And that is a valid macro. Right? It's clear? So now, yep.
Sorry, what
Yep.
dollar? So dollar sign in this context is
Stick in the code that I sent as expression 1. Substitute the code. Just stick it in. It's, what's it called? Substitution, or what's it called? Yeah, interpolation. Thanks, yeah, interpolation. So this is code interpolation. No, before we had string interpolation, and it's the same operator. Is that clear? So let's see if it works. So some counter is 0 until the counter is 10, or until the counter is greater than 10, whatever. Until the counter is 10, I want to print line I plus plus. No, that doesn't exist. I plus equals 1. End. And it doesn't work. Because it says wrong number of arguments in expression starting on line 3, which is, okay, so yeah. So the error messages are not always that precise, right? So actually what the problem is that, so here, how does it know that these 3 lines are the other argument to the macro? And the answer is it doesn't. So what do I need? Begin. And it has to go there. If I put begin there, then it knows that that whole thing is like a block, right? There's one thing. And then it does it. And so I've really got an until loop, my own contribution to the Julia language, right? So if I move the begin here, it doesn't work. So I do have to have the begin over there. So it's not, perfect, because it doesn't really look like a while loop, because I have to have the begin here. I have to have a begin, and I have to put it there. Okay, so that was the solution I came up with. But I mean, I think it's just illustrative of what you can do, right? Just a really simple example of what you can do. Is it clear? Okay. So there are lots of ats all over Julia code. So that kind of makes it a bit ugly in a way, but just get used to it. Compared to Python, where there are no, nasty symbols, except the one that they've just introduced, which is at as well. Okay, so here's a non-trivial example of macros that comes from base Julia, that comes from, one of the bits of base. So the idea is it's called Horner's method for evaluating a polynomial function. So we've got a polynomial p of x, it's just a sum of powers of x with coefficients. And the point is that we can evaluate that efficiently like this. So instead of naively calculating x to the n and then x to the n minus 1 and then x to the n minus 2, which is a lot of multiplications, we just do it like this and it's much more efficient. So the obvious way to do that is with a for loop, but it turns out that if we know, this is important, if we know the polynomial at compile time, then we can write a macro to do it. So this is already implemented in Julia in the math module with a capital M, which lives in the math.jl file with a small m in base. And so the name of the macro, which I don't have access to directly because it's not exported, so if I do using base, which is done by default, it's not available. I can't just write Horner. It doesn't exist. But I can get access to it like this. So that's the answer to your question. How do you put a macro in a module So you just define it there, and then it has a name like this, at base.math.horner. So I just copied it from the source code, and here it is. So hopefully it's not too scary now because we've seen what all the bits mean, right? So I lied, apparently, so it doesn't have to have quote because he's creating the expression at the end of this macro, right? So the macro just has to return an expression. So this expression is going to be a block, which is like a begin-end thing. And okay, so we have to like pick apart this code a bit. Okay, so it's a bit complicated. So how are we going to use it first? So we're going to have some variable x that I can know at runtime, and these coefficients are what I'm sending to this macro at compile time, and I have to know those statically. So those can't be something that I define just at runtime. And so when I do that, so I'm going to have to evaluate this here. And then it does the calculation, and it gives me the polynomial evaluated. So what's going on? So I'm sending it a load of coefficients, and those are sucked up and put, it's like star p again, this splat operator is like star p in Python. So it's sucking up all these coefficients and putting them in one object called p. So p is just going to be an array. And then, so I can access the elements of p as if it were an array. And so I'm going to start off with the last one, which is the, I think I've got it the wrong way around, have I? No, the last one is the highest power of x, yes. So I'm going to take that. So I need to put this esc thing, which is called escaping. So what that does is allows me to access from within the macro sort of variables that exist outside this bit of code. So I haven't got it completely clear in my head. And then we have a for loop. There is the for loop, but the point is that this for loop is going to be compiled away, right? It's going to be expanded, it's going to be unrolled. So we're going to iterate backwards in the polynomial in this array of coefficients. And what are we doing? We're defining this expression. Here's this colon, parentheses operator, so it's an expression. And what do? We take the value of the ith coefficient, and we add it to t times the expression that we already have. So we started off with 1, and we're adding this thing called t, and at the end we do this expression where we first put t is the value of x, and then we substitute and we put the expression there. So yeah, it's really hard to get your head around what's going on. So let's ask it what's going on. So here is what happens, the result of all that macro when you that gets substituted in your code. There it is. So first of all, we do t equals x, and that's some kind of necessary step so that we're not sort of treading on anybody's toes or something. I mean, so that we're not changing the value of x, or I'm not sure exactly why that's necessary. And then that loop has got unrolled at compile time into this sort of static expression that no longer has a for loop. Right. So that's the point. So we're doing code generation from within Julia, generating Julia code from within Julia.
So the JIT must be, like, the first thing that it does, roll through the code, look for macros.
Yeah. Exactly. The first thing that happens, or one of the first things, is to expand the macros. Yeah.
It seems it works even if you don't have S.
Yeah. So there was some discussion about that. There's some reason that you need ESC here. I mean, sometimes it works and sometimes it doesn't, and it doesn't because you don't have ESC. Yeah. So that's why it has ESC. But yeah, I agree. Yeah. If you just do it sort of in isolation, it works without ESC. Yeah. So yeah, I mean, it's really like study it for several hours and sort of it'll gradually go in.
You see anyone using this to
Inference engines, not sure. So I mean, there's an example, for example, in the jump package. So jump is a package, or like a a package for optimization in Julia. Julia for mathematical programming. What's going on with the internet? So it's a domain-specific language. So these macros are enabling me to define new operators that do interesting things in a simple way, right? So there's some documentation somewhere. So hopefully it's just going to give me a simple example. So it just provides the way of making a very simple syntax to define very complicated optimization problems. So creating a model. So yeah, there's a macro to define a variable. You can give it constraints, and then you sort of have these simple things, add constraints. You give it an inequality, and it sort of translates that. The macro translates that into some complicated code that adds stuff and does stuff that you don't want to know about. You just want to write, I have this constraint that this thing has to be less than or equal to 0. And then there's something where you just solve the problem, and it translates all this into complicated code that you would have to write by hand, and that you don't want to write by hand. So that's kind of answers your question, but maybe not exactly.
So obviously you can't export macros.
Yeah. So what was your question again? Inference. Oh, I see. You mean like symbolic computation? So there are some symbolic stuff. Is some symbolic stuff. There's a calculus.jl package that does some kind of symbolic differentiation and things. That's like this. I mean, it's a very first step, but you can do some symbolic stuff, if that's the question. Sort of. Okay. No, I believe not. Oh, I see. But that wouldn't need multiple passes unless it was recursive. No, your macros can have macros in them, yeah. Oh, I don't know. I think so. I'm not sure. Let's try. Time, sine of 10, and begin. Well, I don't think I need the begin, actually. Sine of 10 and time, cos of 10. Did that work? No, that's just doing two separate things. Oh yeah, good idea. Time until I equals. I'm not in the right place. No. Yeah, that's what I was trying to do. It didn't work. Yeah, that's what I was trying to do. Time begin, sine, time cos, end. Yeah, it seems to work. Not sure. Yeah, the time the until would be nice. Yeah, I'm pretty sure you can do it. Yeah. Oh yeah, good idea. So the macro expand always needs an expression. Yeah, so that it is nested here, but it doesn't need a separate pass. It just sticks the code in the right place, right? Okay, yeah. I don't know what it would do. Yeah. Exercise for the reader. Yeah. Okay. So I think that's the end of that section. Is it? I've now completely lost track of where I am. Yeah, so, okay, we're almost finished. So I didn't talk about interop with C. So it's pretty easy. So there's this function ccall, which has this structure. So you have to, well, I wrote it out. So here's an example. So I'm going to call this function with the name clock. So again, it's the symbol from Julia. This shared library, shared C library, this is the return type, and these are the argument types. So it just calls the system clock, and it returns an int 32, which is what it had to return. So I have to know what types I have to pass to the function and what types it's going to return. So a more complicated example, getEnv is going to return sort of environment strings from the system, and it needs a pointer to a char and a pointer to an unsigned char and an unsigned char, right? And so this is the return type. This is the argument type that I'm sending it. So here's a string, so it's going to send a pointer to this string as the argument to this function, and it's going to return another pointer. So when it returns, path is a pointer to an unsigned char string. And so path is this unsigned char string, and then this function, Julia function byte string, actually parses it. Like print it out, right? Until the 0 at the end. 0 terminated. And there is my environment string from the C call, right? So that's pretty neat. So it's quite easy to call, it's very easy to call C and Fortran calls with no intermediate layer. That's all there is to say. They can be pretty complicated return types and everything. So just to finish, where to go from here. So it was a lot of material. So it's going to take a while to process, I guess. So there are not that many resources for learning Julia yet. So this is another one. But there's Leah Hansen has a nice blog where she explores various topics from time to time. There's this Learn Julia in Y minutes, which is just it's that you can learn zillions of programming languages in a few minutes. So it just has really quick examples one after another of how to do stuff in Julia. There are a couple of books of Julia which are in preparation. So who knows, in a few months maybe they'll be ready. The reference manual is really good, but dense. And then there's this Julia users help page. And as I said, the videos of the JuliaCon meeting should be available soon, and that's going to be like another learning resource. So it's still, it is still something that's starting up in a way, but there is now a pretty good head of steam. There were 70 people or so at JuliaCon. It's not going away, and it's going to get better, and all the core developers are really committed to it. So probably the easiest way to get into Julia is to just choose a package that's in your field that that you're interested in, that's going to be useful for you. Just start reading the source code, try and work out how to use it. Start converting all your code start converting your new projects at least to Julia. And so just a random selection of interesting packages. Datastructures.jl has useful data structures. So as a physicist, I was brought up to think that everything is an array. And it turns out that actually basically nothing is an array, right? So this is Fortran has a lot of blame for that. And the lazy.jl does functional programming, pretty nice, a sort of Haskell style thing. Jump is this optimization library I've just been talking about. And Taylor series is something that my colleague mainly has developed. I'm sort of a minor co-author there for n-dimensional Taylor series manipulation for solving ordinary differential equations to high precision, for example. So solving the solar system dynamics for the next billion years and that kind of thing. And Julia was designed, with parallel processing in mind, of course. Haven't talked about it because I don't know much about it, but here's an example. So you can run Julia minus P4. That will run Julia with 4 threads, and then you can just do @parallel, and this, as this is a macro again, of course. So it's going to expand this into some complicated code where it's spawning processes on the different machines and bringing back the results. That's all detailed a bit more fully in the Julia manual. And you can do the calculation. And on this, little laptop, it's much slower to do it in parallel than it is to do it in series. But if you have a decent machine, that shouldn't be the case. So for example, there's this parallel sparse matmul package that does parallel sparse matrix multiplication just using this, as far as I understand, just using this @parallel thing. So that's it. So to summarize, so I think Julia is a very promising new language for scientific computing that solves certain problems. For example, the two-language problem that that people often come across when they're developing scientific code. It's kind of easy to get into from Python. At least the basic syntax, and these more advanced features are maybe not so obvious. And any questions?
How does it work with like large data sets?
So the question was, how does it work with large data sets? So there's an MPF, what's it called, HDF5 module to interact with the HDF5 data file structure that there was a tutorial on yesterday, and it's fine. Yeah, what do you mean? You mean in memory or?
To load like a CSV file, this was like year back, and then
Oh yeah, it should be pretty fast to read a CSV file. I mean, as fast as anything else can read a CSV file.
I had like memory leaks at that time. It's like
With Julia.
2 years back.
Yeah. So, in the Julia world, 3 weeks ago is a really long time, right? It really moves fast. So I had so when I was in JuliaCon, I was in the talks trying to use the packages. I had a 3-week-old Julia and nothing worked because of that. Yeah, so that is a bit frustrating. That was the answer to somebody's question before. You just have to sort of keep updating if you want the latest functionality. Yeah. Or you can just leave all the versions of your packages at a sort of fixed state until something you really want comes along, and then you have to sort of update everything. Oh, so I should have said that. So the package manager to update the packages is package.update, but that actually updates all the packages that you have installed. So apparently that's going to change soon so that you can do more fine-grained, only want to update this package and not everything in case I break something. Question? Any other questions? Oh, yeah, thanks. Yeah, so it is possible to call Julia code from Python, yeah? So in the IPython notebook, there should be a way to use the %Julia or 2% Julia magic function. If you're not in IPython, if you're not in the notebook. Yeah, I mean, you can do it, yeah. I don't know how. Sorry. Yeah, I mean, there's actually a really sort of either neat or ridiculous example, depending on your point of view, where you can do a Fibonacci sequence where Python calls Julia and Julia calls Python, alternating, and it is kind of clever. I decided not to include it because it's a bit too specialized. And because I couldn't get this Julia magic to work. Let me just try again, just in case, something magically changed. But I don't think so. Sorry? I'm an optimist sometimes. % Julia, no. So I have to install it, right? So % load X, and then I don't know what to write, right? There's julia.magic. And then it can't find the Julia magic. Oh, no, there we go. No, and there's an error, yeah. So that's how it should work. So maybe it's just not finding something, right? It's the exception in Julia using PyCall. So, yeah, don't know. Yeah. Oh, yeah, good question. How do you contribute a new package to Julia? So there's this package called metadata.jl that has information like the metadata, that's why it's called metadata, not a very good name in my opinion, about every single package that's registered in Julia. So the first thing you can do is just have a GitHub repository and announce it on the mailing list, and people can easily get it. Oh, so, yeah, should have said that. So there's also package.clone. So that's to just grab a random GitHub repository with Julia package in it, even if it's not registered officially in quotes with this package system in Julia. So So that's the first step. But then if you want to register the package, so with a version number and make it public, more public, then you have to make a pull request against metadata.jl.
But from what I read, Git is the packaging system.
Yeah, yeah. Everything is a Git repo. Yeah.
Is it tied to GitHub, or is that sort of, I mean, could you put it on?
No, you can put it any. No, you just need to put the HTTP address where you have your Git repo. Yeah. When you're doing the clone, when you're doing the, I mean, when you do package.add, that is going to GitHub. Actually, I don't know what it's doing. Yeah. So that's why, in metadata, that the information, so what's in metadata is the information about where, yeah, here we are. So for each package, there's a URL which gives the direction of the Git repository. Right? So you can just put whatever Git repository you want in there, as long as it's publicly accessible. Yeah, thanks. More questions? So I think Julia's really neat. So yeah, try it out. Thanks.